Hey guys, welcome to another AP Calculus AB exam review video. In this video, we will be looking specifically at questions dealing with second fundamental theorem and also extrema on intervals. Okay, so they're going to look like these types of questions is what we ultimately want to understand. So let's go ahead and begin with some basic skills that we're going to need to know in order to be able to do that problem. Okay, first of all, whenever you are asked to take the derivative of an integral, you should immediately be thinking second fundamental theorem, okay? And if you did this the long way, you're basically taking the integral right here in respect to t, plugging in your b and your a value for that fundamental theorem of f of b minus f of a, and then taking the derivative thereafter. That's a lot of steps. The shortcut, and again, you identify second fundamental theorem when you specifically see that you're taking the derivative of an integral. The other key hint is that you're going to have one of these bounds might be in a variable that is different than the variables that are located inside of the integrand, okay? So that's another hint that tells you you're going to use second fundamental theorem. So here's the shortcut. You basically identify the integrands in all of these pieces, okay? So all of these pieces are the integrands, okay? And they're all in respect to t. And let's do A. A is talking about sine of t over t. So the way we're going to start this is we're going to basically recreate the function, and everywhere where we see a t, we're going to leave an open parentheses, okay? Now, you know from first fundamental theorem that you have f of b minus f of a. So essentially, there's a copy that happens, and this is your f of b part, and this is your f of a part, is what's really going on for the shortcut. So the way we're going to work with this is the top, because it's final minus the initial position, the top one will be inserted into this first one, and then the bottom one will be your f of a piece, if you will. Okay, so let's go ahead and do that now. We'll insert x, but then also after we do that, we're going to do it everywhere where t would be located, okay? So our original variable inside of the integrand, everywhere where t would normally be located, we're inputting this upper bound, okay, this upper limit of integration. After we've done that, we're going to multiply the entire integrand piece by whatever the derivative of that top piece is, what that upper limit of integration is. So what's the derivative of x? Well, the derivative of x is just 1, so we're going to multiply that, okay? Now for the other one, this one down here, the lower bound, we're going to plug in 3, again, everywhere where we see a t, and then we're going to multiply by the derivative of that 3. Okay, whoops. So the derivative of that 3 is in fact 0. So you know, since it's multiplication, this is going to zero out and it's gone. But if it didn't, remember it's f of b minus f of a. So don't forget that subtraction sign. So for this one specifically, what would the leftover pieces simplify to? Well, it would simply be sine of x over x. This would be the answer for the first one. Let's look at part B. Again, I'm going to go to the integrand, and I'm going to do this twice. I'm going to say e to the negative something squared minus, again, the same carbon copy, if you will, e to the negative something squared. Now, I'm going to put the upper limit of integration everywhere where I would see a t, and then I'm going to multiply by the derivative of that upper bound, which the derivative of x is just 1. Okay, and you see that it's going to also be the same over here when I insert the lower limit of integration and then multiply by its derivative. And the derivative of a constant is 0, and we know pi is a constant. So this one also zeroes out. So you're just left with this piece here that equals e to the negative x squared with no parentheses. Okay, again, we're just taking derivatives of integrals. Okay, let's look at a couple others. Let's look at C and D. Okay, so let me kind of clear this off real quick. And again, the approach is the same. We're going to look at the integrand. So we have for C, we're looking at 1 over parentheses. minus another 1 over parentheses. That's step 1. Insert the upper limit. So we have x multiplied by its derivative. And then insert the lower limit. We have 1 multiplied by its derivative. This is going to simplify out to 1 over x. Okay, so now let's jump. So d is the same. The only difference is it's our first example where x or our variable is on the bottom limit. Okay, so the lower limit of integration, that lower bound. Look what happens. We have natural log of parentheses squared, technically right there, minus the carbon copy natural log of parentheses squared. We're going to go to our upper limit. So we plug in a 2 and multiply by the derivative of 2, which is 0. Notice that it's the whole integrand piece that gets multiplied. And then now we're going to plug in x and multiply by its derivative, which is 1. So what we're left with here is this zeroes out, and now I'm left with a negative because it was that subtracting that f of a piece, if you will. So a negative natural log of x squared is the answer for D. Okay, so now let's do 2 more because we got to make sure that these fundamentals of actual calculations and writing out the work for second fundamental theorem are sound before we can do those problems that we were looking at when we first started the video. Okay, so let's look at E. Our integrand is cosine of parentheses cubed. Okay, and it's minus another cosine of parentheses cubed. And now when I plug in my upper limit, I'll say x squared goes where t used to be. But then we have to multiply the derivative outside. And the derivative of x squared is 2x. Okay, so let me make that just a little bit clearer right there. This is going to be multiplied by 2x. And then we plug in a negative 5. Whoops, we plug in a negative 5 over here and multiply by the derivative of negative 5, which will zero out. So all this zeroes out, and the answer here is 2x is multiplied with the cosine. And we have x squared raised to the power of 3. Power raised to a power, we know to multiply. So it's going to be x to the power of 6. Okay, so that's the angle for that cosine. And all of this is multiplication. Be careful. Remember, multiplication is there and there. There is no multiplication there because it's the cosine of the angle. Okay, so now let's finish off with f. We're looking at the integrand, which is sine of parentheses to the 4th, minus, again, remember this is the setup for the shortcut, just carbon copy that f of b minus f of a, leaving parentheses where t is at. Let's plug in the upper bound of 17 multiplied by 0. So all these constants, you know they're going to zero out. It's just, are they the first one or are they the second piece? Okay. Now when we plug in tangent of x, we have to remember the derivative of tangent. The derivative of tangent is a secant squared of x. So our answer for this one is going to be a negative secant squared of x. Okay. And it's multiplied. So we're going to say multiplied with sine of tangent of x raised to the power of 4. So if I put parentheses would be located there, and multiplication would be located only there. So the answer would look something like this. Okay, so those are the fundamentals, aka fundamentals of second fundamental theorem of calculus, as far as making sure you understand how to do the process itself. Now, let's go ahead and move on to our warm-up example, if you will. Okay, so we're going to kind of review a little bit of extrema on intervals. And extrema on intervals are talking about when things are increasing, decreasing, concave up, down, all those good things, points of inflection. All of these things are related to that extrema on intervals topic. So now let's see what we're given. Okay. We are given a function called f of x, and you notice immediately, like I mentioned before, we have t's as our variable, okay? Our integrand here is written in terms of t, and our integrand is being integrated in respect to t. And last but not least, we have an upper bound that is written in terms of x. So immediately already, because I see t's in a different variable of x, I'm thinking there's a chance that we're going to use second fundamental theorem, okay? And second fundamental theorem is trying to take the derivative of this, kind of like what we did over here, okay? So if I take the derivative, let's go ahead and do that now because I know we're going to need it later. If I take the derivative of the right side, and I did it just like I did this back here, I would recopy parentheses squared minus 5 parentheses plus 6, okay? And then I would minus all of this all over again. Parentheses squared minus 5 parentheses plus 6. Let's plug in our upper limit. So we have x. All this is multiplied by 1, which is the derivative of x. And then whenever I plug in my lower limit, I have constant, multiplied by the derivative of a constant. All of this will zero out, okay? So this is what I'm going to be left with. This is what I'm going to be left with as far as the derivative of the right side. So I'll say x squared minus 5x plus 6 is that answer on the right side of the equal sign. And when I take the derivative of the left, it simply is going to tell me that that is now f prime of x, okay? So second fundamental theorem helped me obtain that f prime is equal to this function that you see here. Now, let's go ahead and go through the problem. It says, write the equation of the line tangent to f at the point where x is equal to 1. So now, if I'm looking at tangent lines, I already know, and let me go ahead and put part A, that I'm going to have this y minus y1 equals m times x minus x1, the equation of a tangent line, which we know as y minus f of a, x minus a, and f prime at a, okay? So if I'm looking at x is equal to 1, I already know at least that value. But I want to know on f, if I plug in 1 on the f function, what would it spit out for my y value? Okay, so over here on my f function, I'm going to go ahead and plug in 1 where x belongs. Okay, so f of 1 is going to equal the integral from 1 to 1, and I already know there's no displacement happening there. Okay, so immediately my answer is going to be 0. So f of 1 is equal to 0. So we could say f of 1 is equal to 0, aka the point that I just found is input is 1, output is 0. So we have 1, 0 is our point. Okay, so let me go ahead and write that over here. So where x1 is at, we're now going to put 1, and where y1 is at, we're going to put 0. So x minus 1, y minus 0. Now let's find the slope, okay? The slope is going to be from f prime of x. That's going to come from this second fundamental theorem that we immediately solved for at the very beginning. So that means this same at value at that point in time at x is equal to 1, we're going to plug in here and see what it spits out. That's going to be my actual slope, okay? So 1 minus 5 plus 6. So we have a negative 4 plus 6 is going to give us 2. Okay, so this slope right here is going to be 2. So you can leave this as your equation of the tangent line, or if you want to distribute and simplify into y-intercept form, you could just say 2x minus 2. Same thing. Now remember, you do not have to simplify for the AP exam. So this one is more than enough, okay? Let's move on to part B. It says, for what values of x is the graph of f increasing? Okay, so let's highlight some key points. I'm gonna erase a little bit of stuff and we're gonna move on to B just so that we don't get this all mixed up. And we wanna know, when is f increasing and when is it decreasing? Now, immediately with extremas on intervals, I need to remember that f increases when f prime is positive. And I know that f decreases when f prime is negative, okay? We already found f prime, it's up here. We found it from that second fundamental theorem, okay? So we have f of x is equal to, x squared minus 5x plus 6. And we're going to use that to find when f prime is negative or positive. Okay, so let's go ahead and first of all set this equal to 0 because that's important. Okay, we're going to set this equal to 0. So we have 0 is equal to x squared minus 5x plus 6. So we have x minus 6, and then we have x plus 1. Actually, this is going to be a little bit different because we're going to have to be creative with how we factor. Okay, so we know we're going to multiply, not creative, just it's not going to be 6 and 1. It'll be 3 and 2. So x minus 3, x minus 2, those are the factors. And now we're going to see these points, as far as the zeros of these pieces, these binomial pieces are going to occur at 2 and at 3. So we have 2 and we have 3. Okay, so now I can quickly identify, I'm going to be calculating 3 different intervals, and I'm going to test, are they positive, are they negative? And remember, I'm looking at f prime of x. Okay, f prime of x, whether it's positive or negative, that will help me identify if it's increasing or decreasing. Okay, so let's go ahead and use some test points. Okay, so I'm going to use, let's say, 1. I'm going to use 1, which would belong in this first interval. I'm going to plug in 1 here and here in my factored form. 1 minus 3 is a negative. 1 minus 2 is a negative. So I know a negative times a negative is going to give me a positive. Now let's try 2.5. 2.5 minus 3 is a negative. 2.5 minus 2 is a positive, and that product will give me a negative. So let me go ahead and write that right there. Now let's try something to the right of 3. So let's say 4. 4 minus 3 is positive. 4 minus 2 is positive. So that product is going to be a positive. Okay, so I can say from part B that f increases on negative infinity all the way to 2, union from 3 to infinity, because f prime of x is positive. Okay, just like I can say f decreases on 2 to 3 because f prime of x is negative. Okay, so the justification is basically what I just wrote right there. Okay, so now let's move on to part C. Now remember, in order to obtain, before we go to part C, in order to obtain this f prime of x here, I had to take the derivative of this right side. So you could say part of your justification on part B was actually still using per second fundamental theorem. Okay, per second fundamental theorem, we were able to get that f prime, this way up here, f prime of x is equal to that x squared minus 5x. So we've now used that in both parts A and B. So you could say per second fundamental theorem here that you also were able to, and I'm not going to rewrite it, but you were able to use this equation right here. Okay, so now let's move on to part C. Part C is saying find all the values of x where f has a relative max or relative min. Well, we've already done a lot of the grunt work. Okay, so C is identifying when the f prime is changing from positive to negative, we know that f is changing from increasing to decreasing. Okay, so let me write that up here. F of x is increasing here, decreasing of what we just solved in part B, and then increasing again. So if I go from increasing to decreasing at 2, we can say that there's a relative maximum. So a relative max occurs at x is equal to 2 because f prime of x changes, and you can't just say changes signs, you have to be specific, because changing from positive to negative is different than changing from negative to positive. So f prime of x changes from positive to negative. Okay, and then you can see there's a relative min. So a relative min occurs at x is equal to 3 because f prime of x changes from negative to positive. Okay, so it says find all the values of x. That's exactly what we did. The values of x that we just found are x is 2 and x is 3. If it asked us what are the relative max and what are the relative mins, well then we're going to have to plug that into the position function of f. That means we would have to plug 2 to find what the y value is. We'd have to plug that here and here and actually integrate, okay? And then we would have to plug in 3 into the position function, which is here at f of x. So it would be 1 to 3. And whatever that y value gave us, that would be its actual minimum value. Okay, so just remember, the x value is telling you where it's at. The y value output tells you what is that actual quantitative value. Okay, so now let's move on to part D and E. Okay, so it's the same problem, I just copied it over. So part D says, on what intervals is the graph of x or f concave up and concave down? Okay, so f will be concave up. We know when f double prime is positive, aka the same as f prime is increasing. And the reason why I show you this is because sometimes you will be given f prime graphs and you can easily identify if it's increasing, that's where f is going to be concave up. So that's another way to identify that a lot of people tend to dismiss, okay? They always want to go to the second derivative, which isn't necessary all the time, depending on what you've been given. F double prime is negative will show when the concave or concavity is downward, and aka that's the same as saying when f is decreasing, or f prime that is decreasing. Okay, so we know from back here that f of x was equal to all of this right here. Okay, so let me go ahead and just copy it over here. Per second fundamental theorem, we know that this is f prime of x. Okay, so let me go ahead and show this per second fundamental theorem again. And if we want to know when f double prime, oops, I keep erasing on accident. If f double prime is positive or negative, well, then we're going to have to take the derivative up here. So the derivative of the left is f double prime, and the derivative of the right is just basic differentiation, 2x minus 5. Okay, so 2x minus 5, we're going to go down here for part D, and we're going to see the zeros of this second derivative function. Well, x is going to equal 5/2, or 2.5. So all we're going to really do is look at 2.5 and see is the second derivative positive or negative on these intervals now that we're going to test. So let's use this function here, and we're going to test something to the left of 2.5. Let's say 2. So if I plug in a 2 here for x, I'll get 4 minus 5 is a negative. And now if I plug in a 3, something to the right of this 2.5, I'll get 6 minus 5 is a positive. So already, remember, we're looking at f double prime. So we can say f is concave up on negative infinity all the way, is concave up on 2.5 to infinity because f double prime is positive. So f double prime of x is positive. We can also say that f is concave down on negative infinity all the way to 2.5 because f double prime is negative. Now let's finish it off by looking at part E. A common mistake a lot of students make for part E is they think that the point of inflection happens when f double prime is equal to 0, and that is not true, okay? It will equal 0 sometimes, but that's not what makes a point of inflection. What makes a point of inflection is when the second derivative changes signs. Okay? And not only does it change signs, it would have to exist as a point on our original f of x. For instance, let's say that I had an f double prime graph. And this F double prime graph looks something like this. So what's in blue is F double prime. It does change signs. It went from a negative below the x-axis to a positive above the x-axis. But here's the thing. We need to make sure that whatever this value is, let's say it's x is equal to 2, just for an example, that if I plug 2 into the original function, it also would spit out a quantitative number. Okay, it wouldn't spit out something that was undefined, not in its domain. So to be a point, let me highlight that, it has to exist as a point when I plug it into the position function. Okay, to be a point of inflection, it also has to change signs, not just equal to 0. Okay, so let's go ahead and look at E. So it says find the x coordinate of each point of inflection. So all I need to do is see, when does the second derivative change signs? Okay, so we know that the point of inflection could occur at 2.5. Whoops. I just have to make sure that if I plugged in 2.5 into the original f, would it in fact give me an answer? And it will. There's no undefined piece going on here. Okay, so my point of inflection, and all it's asking for is the x coordinate. We're going to say the point of inflection, so per definition of point of inflection, the POI occurs at x is equal to 2.5. And you're going to say because f double prime changes signs. Now, you don't have to say changes from positive to negative or negative to positive specifically the way we did back here on part C with relative max and mins, because there's a difference between a max or a min. A point of inflection is a point of inflection. Whether it's this way or whether it's this way, it's still a point of inflection. So just the fact that you're just mentioning changes of signs, that's good enough.